Okay, this last part, this lecture 25, we'll be talking about primordial nucleosynthesis or Big Bang nucleosynthesis. Uh, in our universe, we see mostly hydrogen, which is the simplest atom, but very little of the heavier elements, which can all account for as having been synthesized inside a star, were then explosively ejected into the interstellar space. On the other hand, everywhere we look, besides hydrogen, we also see a significant amount of helium. The helium abundance can be deduced from the measurements of intensity of the spectralized helium-4 in the stars and planetary nebulas and galactic as well as extragalactic H2 regions. The data indicates helium-4 the mass fraction close to a quarter. It means all the mass uh, basically it's hydrogen plus helium and divides the helium amount of helium in the mass ratio, we'll call it Y. Observer Y is about 0.24, 0.25. Similarly, we can observe much smaller uniform abundance of other light elements. Deuterium, which is the isotope of hydrogen with an extra neutron, helium-3, and lithium-7. These light nuclear elements are theorized to have been synthesized in the early universe by the path we're going to describe. So these are the Big Bang nucleosynthesis or the primordial nucleosynthesis we're talking about. First, we'll talk about the epoch called proton-neutron equilibrium or freeze out. About 10 microseconds after the Big Bang, when the thermal energy was about 200 MeV, quarks have coalesced into nucleons and unstable particles have vanished from rapid cooling of the universe. The cosmic soup was then composed of protons, neutrons, electrons, positrons, three flavors of neutrinos and the antineutrinos, and photons. Sometimes we call this the era of nucleons. Up until the first second after the Big Bang, neutron and proton could interconvert to each other by weak interactions. For example, neutron taking a positron can become a proton plus antineutrino, or backwards. Antineutrino adding interact with proton can produce neutron and positron. Same way, uh, this reaction also. So neutron protons are in thermal equilibrium. So the number ratios, it's the number of neutrons divided by the number of proton, called lambda, is governed by the Boltzmann distribution. See, the number is proportional x e to the minus energy divided by kT. And so therefore the ratio neutron and proton will be the e to the minus electron energy minus neutron energy minus proton energy over kT. And the energy mostly is rest energy, so the neutron energy will be just the rest energy neutron mc squared. So and here you just plug in the neutron proton mass difference, 1.3 MeV, neutron slightly heavier than proton, and you get this. So the number ratio should be in thermal equilibrium should be given by this if you know the kT. When the thermal energy fell below so-called the freezing point, uh, which is about 0.7 MeV, MeV convert into uh, temperature-wise, just divide by Boltzmann constant, you get about 10 billion Kelvin, and this is about 1 second after the Big Bang, because knowing the temperature, you can plug in this formula, you get the cosmic time. It's around in term seconds, about 1 second. Now the interconversion rate, gamma fell below the expansion rate h, so that's how people arrived at 0.7 MeV. Now, once you know the fact that this is uh, uh, KT is 0.7 MeV, so divide that to 1.3 MeV, and e to the minus work out to be 1/6. Okay, and this number will subsequently drop a little bit due to neutron beta decay. Free neutron can decay into proton plus electron neutrinos, but not too rapidly, since the lifetime of free neutron is 880 seconds, which is of course much bigger than the age of the universe then. Okay, about a few seconds. So it's only dropped a little bit. So now we can talk about uh, the fusion of neutron proton uh, into bound nuclear states. But early epoch, as soon as they were formed, for example, they were immediately blasted apart by energetic photons, so it's photodissociation. So the question is, how do helium-4 formed? So the idea is that a proton-neutron fuse into a deuterium, which is an isotope of hydrogen, and produce a photon. Or can reverse, an energy photon can photodissociate this deuterium and go back to neutron proton. So all these reversible processes until uh, the universe cools such a way that the photons, the ambient photons, is not energetic enough to trigger the reverse reaction. So therefore, proton neutron turns into a deuterium, and the deuterium combines with another neutron, an emitted photon, to become a tritium, the isotope of hydrogen with two neutrons, and then combine with another proton to form helium-4. Okay. And these fusion reactions will not go further to form heavier nuclei, as helium-4 is a particularly tightly bound state, and the formation of nuclei with 5 nucleons is not energetic favored. For the lacking of a stable mass 5 nucleus, the synthesis of lithium with mass number 6, 7 from stable helium requires a much less abundant deuterium. So you have to find the helium for to find a deuterium to make a new lithium, or to find a tritium to form and the deuterium is very few of them, so therefore it's hard to so they can be produced but very small amount. So the Big Bang nucleosynthesis could not progress further to produce even heavier, for example, for mass over 7, because there are no stable mass number 8 elements. For example, beryllium 8 almost immediately disintegrate into a pair of helium-4s. So how the heaven, but only in the stars, when the packed very high concentration of helium-4 at extremely high temperature, can mature stars proceed to form stable carbon-12. So basically, with all the heavy elements, carbon, or those are produced inside the stars. But here, helium and deuterium, lithium, they were produced in the Big Bang, or in the early stage of the universe. So we can calculate the helium-4 abundance. Okay. I said, detailed calculation, thermal energy was the gamma condition tells the Big Bang nucleus stops at 0.1 MeV. And the photon no longer energetic enough to photodissociate bound nuclei. This corresponds to the temperature about 10 billion, about a billion Kelvin, and the constant time about 100 seconds. So then, remember we talked about all this. You can combine all these states step, but the net effect of all these fusion reactions leads to basically the formation of helium-4 is combine two neutrons and two protons into helium-4 plus gammas. Now there are more protons than neutrons, so therefore, basically all the neutrons are end up in heliums. So therefore, the number of neutron is equal to twice the number of helium because helium contains two neutrons. Uh, the number density of hydrogen and which are the leftover from all the others, it's all the protons that can be combined helium. What's left over is the free protons, and so the hydrogen atom is equal to the number of proton minus the number of neutron. Left over become the hydrogen atom we see today. So now neutron proton basic mass is the same. We call it nuclear mass, and the helium had two protons, two neutrons. Is four mass is four times nuclear mass. So therefore, the mass fraction, why remember we said about, is the mass of the helium divided by the sum of the proton or hydrogen plus helium-4 mass. Okay. So therefore, the mass of the helium-4 is number of helium-4 times the mass of helium and the individual helium atom. And same way, the hydrogen is number of hydrogen times the mass of the individual hydrogen. So NH sub Eg is, remember we talked about this, is half of neutron number, and number of hydrogen is proton minus neutron. So, and the mass here is four times, and of course hydrogen is just one proton, is just so one nuclear mass. So now you can see if I cancel all the nuclear mass factors, and top is 2 divided by 4 divided by 2 is 2, and uh, uh, and then the whole thing divided by number of protons, so it become n sub n divided by n sub p become lambda. Same way, this is divided by p is 1. This minus 1, so this is minus 1, this is plus 2, so it's plus lambda. Okay. So therefore, the mass fraction of helium is 2 lambda over 1 plus lambda. Lambda is ratio of the neutron over proton number. And remember we said that the ratio gets is about 6, and then because free neutron decay, it diminishes to a little bit, go to lambda 1/7. So if lambda is equal to 1/7, you plug in here, you get exactly 0.25. That's just very close to the observed ratio. And this, of course, is a very crude calculation. More detailed calculation, Boltzmann equations and things that will be obviously more precise. Reaction rates. In summary, once the deuterium was formed by fusion proton-neutron, this chain of fusion reaction proceeded rapidly. So that's by about 200 or 180 seconds after the Big Bang, just about all the neutrons were bound into heliums. Since this reaction was not perfect efficient, there are still traces about deuterium and helium-3 are left over. Formation of nuclei beyond helium progressed slowly because only a small number of lithium-6 and 7 were synthesized in the Big Bang. I'll explain this diagram later. So the crude calculations presented here are just for illustrative purpose only, but realistic calculation would consider, for example, the fact the standard model assumes 3 flavors of light neutrinos: electron neutrino, muon neutrino, tau neutrino. This affects the effective degree freedom. Remember, the Kantian spin degree freedom in the radiation energy density. Its value has impact on the expansion rate. making it freeze out earlier, hotter, thereby increasing the neutron-proton ratio and affects the helium fraction. So uh, so the fact you had to take the fact there's three neutrinos. In fact, the first some evidence that only three light neutrinos came from cosmology, not came from particle physics uh, experiments. Also, this light element abundance turns out depends on the baryon mass density, okay? Because it affects the cooling rate of the universe. In particular, deuterium is particularly sensitive to uh, the baryon mass density. Thus, the observed abundance of deuterium, uh, one every 300,000 hydrogen, constrains what this value would be. Uh, it was here is a plot, okay, of theoretical calculation of helium. Okay, here is the 525, but it turns out this was said this fraction depends on the baryon density. Okay, rho sub, rho sub b, and so helium depends not too strong, but it depends on it. The most strong dependence is deuterium. See, it really depends on the value of the baryon mass density, and helium 3 also depends on, but not again not too strongly. Lithium depends more strongly. Okay, now these curves are the theoretical curves, and the vertical width, vertical height, if you want, is observation uncertainty, and term is very well defined, has very narrow. Okay, so therefore this box indicates uh, the value of baryon mass density, and that's compatible theoretical predictions. Okay, same because determinant depends on it's a very strong dependence, and it's very well measured, so fix the baryon mass density very well to a narrow range. And here it's not very good, but lithium is also not very good. So mainly it's the determinant that determines the value of the baryon density to be 4.19 to minus 31 gram per. Now the same way is in terms of the omega. So the density parameter is about 5%. Okay. Or in fact, by the way, this graph is kind of old, about 10 years, more than 10 years old. So now the value drifted a little bit more towards 5%. Now compare the total mass density. Remember we said it's 0.31, and this shows that the ordinary atomic mass, the baryon, is only a small part of the matter in the universe. Now, once you know from here knows the baryon mass density, you can divide it by the or proton energy. So the baryon density is the parameter omega b times the critical density divided the proton energy based on rest energy. So that's 939 MeV, and this 0.5% times the critical density is about 220 MeV over per cubic meter. So you get 0.2, about a quarter for cubic meter. So therefore, the baryon number density is about 1 proton in every 4 cubic meter volume. Okay. Again, it's an extremely small number. Okay, we'll talk about the lesson we learned in lecture 25. We said the radiation distribution is the standard which we learn in statistical physics. Is the G is the spin degree freedom divided by a factor e to the kt, +1 for fermions, -1 for bosons, like photon. And the radiation number density is, if you integrate that, basically this is the end, you get proportional temperature to the cube. And same way, if you sum up the total radiation energy, then the energy density is proportional to the fourth power temperature. That's the famous Stefan-Boltzmann law. And we also learned that the temperature scales like 1 over A, and so therefore E scales like 1 over A, KT scales 1 over A, so therefore the combination E over T is scale invariant. So this distribution do not change even though the temperature getting cooler, lower, but the distribution is still the same. And easy to remember the fact you can, from the temperature, you can figure out what cosmic time was the radiation was. This is so cosmic history is composed of series thermal equilibria, and the transition time is determined by the, the reaction rate versus expansion rate. And from this, we can form a chronology of the universe. And the Big Bang nucleosynthesis can account for abundance of light elements, helium, deuterium, lithium. And from this, we can deduce the baryon density, omega b, or number density, number of baryon per unit volume. For next lecture, we're going to talk about decoupling photons when the universe becomes transparent to light. And so these are the primordial light, or primordial photon, which is the cosmic microwave background we detect today. Also, similarly, there's decoupling of neutrinos. So it turns out you can calculate the comparable number of primordial photons and neutrinos, so about 400 per cc. The 400 photons, 400 neutrinos per cubic centimeter in the universe.